ହେଇଗଲା। ହଁ ୟୁଟ୍ୟୁବ ଗଲି। ଏକ୍ସଲେଣ୍ଟ। ଆଜ୍ଞା ଗୋଲ ହିଁ ମାରିଥିଲି। ଆସିଲା 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 ଆସିଲା।
ଅଛି ମୋ WhatsApp में और सर्च कर देबे WhatsApp तो WhatsApp पर लॉगिन है
ठीक है सर ठीक है हाँ ହେଇଗଲା ଚାଲ
ठीक ଅଛି
ନାଇଁ ନାଇଁ ହେତିକି ଏଇ କଥାଟା ହିଁ କହୁଥିଲି। ଅଡ଼ିଓ ଦେଇଛ ଏଇଠି
ବଢିଆ ଯାଉଛି।
ନାଇଁ ଏଇଟା ସବୁ ଲାଗି ଅଛି ଆଉ କିଛି ପଢା ହେଇନି। ଓବିଏସକୁ ଯାଇ କଣ କରିବୁ? ହଁ
ବଢିଆ ନଉଛି ବଢିଆ କ୍ୟାପ୍ଚର ନଉଛି।
ଅଡ଼ିଓ ଇନପୁଟ କ୍ୟାପଚର କଣ? ପ୍ରପର୍ଟିଜ
ଫିଲ୍ଟର
ନାଇଁ ମାଇକ୍ରୋଫୋନ ଆର ହଁ ବ୍ଲାକ୍ ମ୍ୟାଜିକ ମାଇକ୍ରୋଫୋନ ଏରିଆର ଇଣ୍ଟେଲ ସ୍ମାର୍ଟ ସାଉଣ୍ଡ ଟେକ୍ନୋଲୋଜି ଠିକ ଅଛି।
ସ୍ମାର୍ଟ ଟେକ୍ନୋଲୋଜି ସାର୍ ଏଇଟା ୟା ନେଇଯିବ ଲାପଟପ୍ ନେଇଯିବ ଏଇଟା ନେଇଯିବ।
ଲାପଟପରୁ ଯିବ ବା
ଆଉ କୋଉ ସେ କଲର ମାଇକଟା ଦେଇଯିବ
କଲର ମାଇକ ଏଇଠି ମାଇକ୍ରୋଫୋନ ଏଇଟା ହଉଛି ମାଇକ୍ରୋଫୋନ। ହୁଁ
ଲାଇଭଟା ଦେଖେ
ମତେ ଲିଙ୍କଟା ପଠେଇଲୁ କାଟିବା
प्रोजेक्ट
सर पॉइंटर लास्ट
এটা এটাই okay audible no no okay good morning all last class we basically looked into something that is related to chemical kinetics, right, and how it is associated with heat release rate, okay, and how it plugs into the species conservation equations and energy conservation equations, okay. So the rate at which a reaction takes place in a combustion zone is going to dictate what is the net heat release rate that is happening during the process. Okay. So that was all based on gas phase reactions that we're looking at. And today what we do is we bring that combustion phenomena to what happens in batteries, specific to batteries, what is the mechanism of initiation of the battery fire, and where that kinetics component comes into the picture. All right, and using that component, how can we build models about that? So what we will do is look at what is the basic mechanism of a battery fire, and then where these models of kinetics plug into. Okay. So to start with, let's have a look at some statistics. Okay, so in the recent years, what is happening to the battery-based energy storage? So before this, most of our energy storage was in the form of fossil fuels. Still, energy usage. Still, till now, we have majority of it is still based on fossil fuels like coal, oil, or gas. But if you look at the trends, recent trends like 2020 to 2023 and onwards, you see that the usage of battery as an energy storage is increasing significantly. It is taking an exponential growth. Still, this is a small fraction of the total energy storage that is being done, but the trend is growing exponentially. Okay, so basically, this is battery storage capacity addition in terms of gigawatt annually. So in 2023, there is almost 40 gigawatts of energy storage that has been added, which is being stored in batteries. And where are we seeing these application of batteries? So on the right hand side, you basically see like 2023, you can see that most of the battery usage is happening in electric vehicles, four-wheelers, two-wheelers, three-wheelers. We are using batteries in our electronics like phones and laptops, but still, as with the rise of electric EVs, the application of battery or the demand of battery energy storage devices is increasing. So that is taking a majority of the chunk. Now, if you take a forecast to 2030, so the NZE means net zero emissions. So it means that you basically get rid of all fossil fuels. If you're converting to all energy storage devices are based on, or energy devices are based on net zero emissions, then the usage of battery, the demand of the batteries are going to be very, very high, and most of its application is to electric vehicles. Okay, so it could be two-wheelers or four-wheelers for any form of electric vehicles. This takes into account. Utility scale batteries are large scale battery storage systems, energy storage systems, megawatt, gigawatt scale energy storage systems, particularly for data centers and power storage devices, right? Grid scale and storage devices. So that is also increasing, but we see that where most of our batteries are going to be used are in the vehicles, okay, in the form of EVs. Now let's look at this. These are some additional statistics that we want to look at to get an idea about the trend. So what we are seeing here is what is the investment happening in which sector are venture capitalists investing, okay, in the future, or what kind of technology. So in e-mobility, if you look at this, so these are basically different components where like that are associated with the battery propulsion system, okay, in an electric vehicle. And these colors are basically different countries. Okay, so if you look at things like battery recycling technology or battery reuse technology, so US is basically investing a lot of money into that aspect. Okay. Similarly, if you look at battery management systems, so these are basically looking at the battery health, monitoring that, and giving inputs about the status of the battery. Again, a lot of investment is happening in that. Now, if you look at the other components, so if you look at India, so this is the yellow bars basically represent what India is investing into. So what we are doing is we are basically utilizing those batteries in two-wheeler, three-wheeler components. As it is, you can see in daily life, you can see these two-wheeler EVs are increasing drastically. Okay, so that is where, so it does not show the scale of investment, but the relative scale of investment. So most of India's investment is going towards making these two-wheeler or three-wheeler EVs. All right, and if you look at truck, bus, and commercial, so like for large heavy vehicles, so India is not investing yet. Okay. Yeah, recycling as well, India is not investing. Battery management system, there are small investment. Battery manufacturing, small investment. Battery component manufacturing, no, not yet. Still, we are dependent on importing these components and then use them to manufacture. But still, this is a very small component. What we are mostly doing is getting the importing those batteries and then implementing it for applications. And I think, yeah, if you look at two-wheeler, three-wheeler, yeah, four-wheelers, again, we are not investing much into those technologies. It is all about integration of the components. Then charging infrastructure, yes, we are investing, but this is still a small component. And car making is still very small. So what we need to do is, as like our how it is going to impact India in the current stages, looking at the applications of these electric like battery operated vehicles, especially in the two-wheeler, three-wheeler segment. And as it is going to expand, it is also going into USC four-wheelers are also now coming up that is powered by battery electric vehicles, right? So along with this, these components, what it means is the technology that we are getting from like other countries. Those countries have designed or studied the health of the batteries based on their conditions. Okay, some standardized conditions that are applicable to their environment. Okay, still they may not be suitable, may not be optimized for Indian scenarios, Indian drive cycles or Indian ambient conditions, things like. So that is definitely a thing that we also need to investigate or explore in terms of our national scenario. All right. So the largest, I think, investors, if you see in all these sectors, is United States along with China. All right. China is also investing equally, if not more, in United States compared to United States in certain sector. Okay. So this is basically the investment scenario between 2018 to 2023, and this is definitely going to accelerate further. Yeah, so these are the regions where we are at. So mostly India is investing in the developing the electric mobility fleet, and most of it is into two-wheelers or three-wheelers. Okay, so now if you want to use these electric vehicles, typically lithium-ion batteries are the ones that are being preferred. Okay, so these are lithium-ion batteries are currently the cornerstone of these electronic devices, especially for mobility, electric mobility sector. So what is the reason is basically you have a very high energy density for lithium ion batteries compared to the other forms of batteries. Okay, so it has a low internal resistance and a high energy specific energy density, which is critical. Already batteries, if you compare it to conventional fuels, the energy density is lower. Dynamic energy density is lower. So among that, we have to pick the highest, the model that has the highest energy density. Okay. But if you come down and you look at the safety requirements for this kind of lithium ion based batteries, there it is mandatory to have protection circuit. Okay, that manages the health of the battery. All right, so this is very important. So now electric vehicles basically are accounting for 90% of the battery usage that we have seen. And the commonly used batteries are basically cylindrical sizes, 18650 and 21700. These are typical configurations. So if you look at this, so these are 18650, 21700 type of cylindrical cells, lithium-ion batteries. And these are primarily named against the size, the dimensions of the battery. So 18 mm dia and 65 mm is the height of the other cylinders. So you can see that 21700 is slightly thicker and slightly larger in length. If you look at these two comparisons. Now these are 4680, so 46 mm diameter and 80 mm length. These are recent ones that Tesla is using in some of their high-end cars, and they seem to be more resistant to battery failures compared to the smaller ones. But still, these are not being currently used in our Indian automotive sector. Okay, so if you look at the structure, a cylindrical battery cylindrical cell, so what you see is you see layers of your cathode, anode, separator, along with the electrolyte in between. So you have arrays of cathode, anode, alternating arrays of cathode, anode with electrolytes and layers of electrolyte and a separator in between. So they are like wafers which are being rolled in the cylindrical format. All right, so this is the typical configuration of the batteries or cells that we use. And then we stack these cells in cylindrical arrays, either in hexagonal form or cylindrical form, so that you get a battery pack. Okay. So the typical materials that we use for the cathode electrodes are your some kind of oxides. So these are, you can see, these are lithium iron phosphate oxides. Okay, so nickel, manganese, cobalt oxide, NCS, lithium, nickel, cobalt, aluminum oxide. So these cathode materials are typically oxides, or mixture of oxides. All right. The anode is typically graphite or graphite with silicon oxide, and electrolyte is typically some carbonates, like solvents, carbonates like ethylene carbonate, okay, dimethyl carbonate, ethyl methyl carbonate, diethyl carbonate. Okay, so typically it will be something like, so carbonate CH3, and this is, okay, so you have no, sorry. Okay, so this is your EC, so ethylene carbon. So you have a carbonate functional group along with the ethylene C2H2 component. All right. So yeah, so again you have dimethyl carbonate, ethyl methyl carbonate. So each of them are basically having some functional groups attached to these oxygen atoms. So this is a dimethyl carbonate. So you have, sorry, so you have two carbon atoms attached to the oxygen atoms. Okay. So this is a dimethyl carbonate. So you have two methyl groups with a carbonate. Okay, so these are basically acting as solvents in the electrolyte, and then lithium salt is used as a solvent. All right. So looking at this, what do we realize inside this battery? What do we realize looking at these compositions? We see that if you just recall combustion and ignition, we see that this particular device or system has oxidizers, okay, present within it, as well as combustible materials, right, within the system. So basically this kind of a cell both has potential of like oxidizing as well as reducing components. Okay. So now, if you look at the recent reports on EV fires, all right. So these are very recent, 2023 to 2025, they were published. Okay, so two-wheeler EVs, some reports of battery fires have been given because of battery overheating. Right, smoking, melting, or fire kind of incidences have been reported, and so these kind of incidences were reported. This is in 2025. And then in UK, there were a record of over 200 e-bike, e-scooter fires that were reported. Okay, so many occurred indoors with some serious consequences. So mostly these electric vehicles, either you are charging indoors in the basement or they are in the showroom. Okay, so they are not open in open environment. So closed environment. And then you have showroom fires in India. So for two-wheelers, so around 70 e-scooters plus 100 plus battery sets were there in the showroom, and they got damaged. And this, the reason for this also you have to notice. So the reason was not because of battery failures, but because of some electrical failure, is what was reported. That triggered, and batteries being combustible because they have oxidizer and hydrocarbons can burn severely. Then again in India, I think this was in Karnataka. So There are more than 80 EV fires reported, and some of them, some statistics are also given. Some of them are due to power leakage. This could be faulty batteries, low quality manufacturing, battery explosions, and accidents because of mechanical abuse. Okay, and in Australia, like 2 cars were destroyed because of some mechanical abuse that happened to the batteries. Okay, so what we see here is the numbers. If you compare it to conventional IC engine vehicles, the numbers are not that large. Okay, these are still rare in occurrences compared to, or the likelihood of a combustion of a, or a battery fire is less likely compared to a fossil engine or an IC engine vehicle. Okay, however, the severity of these fires, or the chance of extinguishing these fires is challenging. Okay, so now let's look at the mechanism through which this battery fire happens. All right. So you basically have an anode, then you have a separator, not a separator. There's an interface that is generated between the anode and the electrolyte. So a solid electrolyte interface. Then you have the electrolyte. Then you have a separator. Then the electrolyte on the cathode side. Then you have another interface layer between the cathode and electrolyte and the cathode material. All right. SEI is solid electrolyte interface. Okay, so it is, yeah, this is cathode electrolyte. So these layers are not very thick. They are nanometers, few nanometers thick, and they will develop in the first charging or discharging cycle. Once the electrolyte starts to interact with anode, it forms some kind of a protective layer. So it acts as a protective layer that inhibits continuous reactions between the anode and the electrolyte. What else is that is cathode electrolyte interface. All right, and the separator basically stops it from short circuiting. Okay, so it is basically some kind of a fabric that does not allow these two electrolytes to interact with each other. Okay, so now if you look at the temperature, so when you are charging or using the battery, there is current flow happening, and because of internal resistance, there could be localized heating that is taking place in these batteries. Okay, so once your battery temperature reaches around 69 degrees Celsius, okay, your SEI decomposition starts. So this protective layer that is initially formed, okay, so this starts to disintegrate uh, at temperatures starting at temperatures of 69 degrees Celsius. Okay, so once this layer basically disintegrates, your electrolyte and anode starts to interact with each other. So it starts to take away the lithium ions from the anode, and these reactions are basically some sort of exothermic reactions. Okay, so they are generating some amount of heat, even if it is small amount of heat, but still it will start generating some amount of heat as the SEI decomposes and the electrolyte interacts with the anode. Okay, so as the decomposition starts in the temperatures get like it heats up, as it reaches 100 degrees Celsius, the electrolyte anode reaction starts to take place vigorously. Right, so this electrolyte and the anode, they will start to interact once the heat is being accumulated and reaches a temperature of 100 degrees Celsius. Okay. Now, because of these all reactions, it leads to heat generation. So further heat is being generated because of these reactions. So as the battery temperature will reach, once the battery temperature reaches 130 degrees Celsius, the separator, the separator basically disintegrates. So the green zone, that is basically your separator, will start to this guy will now start to disintegrate. It is no longer maintaining. So what this leads to is an internal short circuit, okay, between the anode and the cathode. Okay, so now when there is a short circuit, now you have a path of low resistance. Now very fast reactions will start to take place, and so these are now all of them are exothermic reactions. So now these will lead to electrolyte decompositions because of very high temperatures. Now these electrolytes will decompose, start to produce decomposition products, and ultimately as it goes to 300 degrees Celsius, because of further heat rise, your electrolyte cathode reactions also start to take place, and because of this you will now have oxidizer release. Okay, so if we just recall, so most of the oxides are at the cathode side. Okay, and the electrolytes are basically sources of oxides as well as some hydrocarbons. All right. So now as the process heats up, okay, so like we start with the lowest temperature, 69 degrees Celsius. These are the interface layer between the anode and the STI. So they will basically disintegrate, start to react and starts producing heat. And till you reach a certain temperature, that is 130 degrees Celsius, you will get an internal short circuit, which then leads to like a chain reaction. It leads to electrolyte decomposition, starts to produce these free radicals, and then the temperature further increases and goes to 300 degrees Celsius, leading to electrolyte cathode reactions. And then it will basically release oxygen. Now you have oxygen as well as these kind of free radicals hanging around at 300, 400 degrees Celsius. So that now leads to a fire. Okay, so that will start the vigorous combustion process. Okay, so this is the process in which your thermal runaway failure typically happens. Okay, so like thermal runaway is basically a condition that heat generation rate exceeds the heat removal rate. Now during this processes, okay, so during this processes, like the SEI decomposition happens because of lot of usage, discharge and cycling and discharge cycling, cycling routines. If your heat extraction, so there is some heat that is being generated. If your heat extraction is happening sufficiently well enough, then your temperatures will not rise. Okay, but in cases in packing, in certain packing, if your heat extraction is not efficient, then this local heat accumulation will take place inside the cell, and that will lead to your ultimately lead to your battery failure. Okay, so basically a condition where your heat generation rate exceeds the heat removal rate, that will lead to an uncontrollable temperature rise, ultimately leading to battery fires. So now these are happening at a very fast rate, rapid, localized, because it happens within a cell. Okay, so all of these processes are happening within inside the cell, so it is very localized. You cannot see it outside. And once you have a battery failure, a cell failure, then the fire that has happened to one single cell, now that heat will be transferred to the adjacent cells, because these cells are very closely packed to each other. So that will lead to a cascading effect where one cell failure leads to the failure of adjacent cells. All right. Okay. So now there is a coupling mechanism. So this is what happens to a cell when you are increasing the temperature of a cell individually. All right. But what happens is, as we are using the cell batteries with charging and discharging cycles, there is a progressive performance degradation. Okay. So as you use more and more batteries, the batteries will degrade. The internal resistance will increase. So with the same heat current, if you extract the same load, your temperatures will rise because of heating. All right, so let's look at this one. So these are happening mainly slowly. As you are using the batteries, the health of the batteries are decreasing. So battery aging because of constant usage. Then during charging or discharging, there might be mild overcharge, so it is heating up slowly. Then there are material degradation of all the components like the separator, the anode, cathode. Then the SEI instability. So the solid electrolyte interface that is basically acting as the like a protector between the anode and electrolyte reactions happening continuously. So because of usage, these layers might get unstable. And also there is something called as a lithium dendrite formation on the anode side. So you might form with usage, lithium ions might stack up like and form dendrite-like structures, right? And that might pierce locally. That might pierce locally these SEIs and can induce some local reactivity. Okay, so these can happen with over the time as you are continuously using the batteries. All right. So now because of these aspects, okay, so because of these kind of material failures or reduction in quality of the materials, your risk to safety failure will increase. All right. So what are the aspects of safety failure? So safety failure are something that are related to accidental. So accidentally, if there is an internal short circuit, so you start supplying high amounts of current suddenly, so that leads to heating up. All right. So internal short circuit or an external short circuit or some kind of external mechanical. So there's a piercing in the battery that basically disintegrates the structure of the battery, or there is a heat abuse, so it is under, or it has overheated, or there is a severe overcharging. So these are kind of accidents that can lead to battery failure. Okay. Now, if your quality of the health of the battery is is good, or the material quality and the build quality is very good, then your risk to safety failures are lower. Right. So when you purchase a new battery, when it is brand new, everything is perfect. So the structural stability, integrities are good. So in that case, the risk to these kind of failures is low. But with usage, the quality of, there is a degradation of the quality of the battery, and that will increase the risk to safety failures. So now in the initial stages, probably a certain degree of mechanical abuse would not have led to like overall battery failure. But if the batteries are like 5 years, 7 years old, has been used continuously, then that particular same amount of mechanical abuse can lead to a battery failure. Internal short circuit is the separator going down. External short circuit is basically the load is not there. So now if you have connected the anode cathode directly without any load, so there is now a high amount of current going in. So if the high amount of current goes in, so because of resistance it will heat up, right? I square R, right? So that will lead to heating up of the battery. So okay. All right. So these are the, so as you use the batteries more and more, the risk to safety failures also increases. Okay. Alternatively, now let's say you have a battery and that has been constantly undergone heat abuse, so it has been heated significantly through different cycles. So because of the heating also, it can cause some kind of a material degradation inside the battery. Okay, so constant overcharging or some minor short circuits and things like that can also lead to disintegration or degradation of the components inside the battery. Okay, so that will basically lead to performance degradation. So your battery life is going to decrease if you are not using the battery in the optimal conditions. Okay, so safety failures can lead to permanent performance loss, and this, because of this loss, it will basically make it more prone to overall battery failures. All right. So this is basically coupling mechanism in which your lithium-ion batteries behave throughout its life.
Sir,
Yeah.
sir, what is the after the lithium dendrite formation, how it will affect the performance of the
Lithium dendrite formation. So basically, if you look at these, this is a very thin layer interface that basically separates the anode and the electrode. Okay. So now because of constant, like, so your lithium ions are during the discharge cycle are going from anode to cathode and cathode to anode during the charge cycles, right? They are basically moving around in the electrolyte depending on the cycle. So as these guys come back, they might stack upon each other instead of all of them infused into the anode. They might stack upon each other and create this kind of a dendrite-like structures. Okay. So now what that will do is that will create a local pathway of interaction between the electrolyte and the anode. Okay. And these kind of structures might also affect the separators. So if the structures are long enough, then it can also affect the separators. Okay. So in that way, it is basically affecting the structural integrity. Okay.
Yes, sir. And this is internal short circuit and external short circuit.
So internal short circuit. Okay, so now if you correct, so okay, so now if you are connecting it to a load, right, to a motor, let's say, so this basically draws some current, takes the adequate work output, and then the current comes through this cathode, right? Now, if you so there is a resistance to the load or an impedance to the load. Now, if you remove that, so there is a low resistance pathway, so the high amount of current will flow through. Okay, so that is like an external structure. Internal short circuit is, these two are separated by the separator, right? This does not allow it offers some kind of a resistance, right? So that these two things will not interact. Now, if the separator basically breaks because of high temperature, let's say 130 degrees Celsius, then the anode and cathode side are basically coming in contact internally. Okay, so that is basically your internal short circuit, ISC. Sometimes you will see in the reports it is written as ISC. Yeah.
Can we measure the after
So that is the challenge. How do you, so the gap is there. A lot of studies have been going on. How you analyze the state of the health of the battery. Okay, so looking at various like charging cycles, discharging cycles, there are studies that are That is research that is going on to get more quantitative information about the material health of the battery. Okay, but that is an ongoing thing. Okay, so we'll look at the challenges and what is the scope of work that is going on. But yes, that is one of the aspects where you want to monitor so that you can clearly say if the battery is good or bad. Okay, so now we know that this thermal runaway mechanism is basically leading to the battery fires and it is a catastrophe. Okay, so now you have a fire, and with conventional fuel fires, you know how to extinguish these fires. Okay, but what is the challenge of EV fires? Let's have a look at that. So first of all, battery fire initiation is happening internally, right? With the SCI breakage, separator breakage. It is happening. Everything is internal. So from outside, you will not be able to detect any of these kind of features, the initial feature. So that leads to a delayed detection. Unless your battery temperatures are going very very high, or you are actually seeing some kind of a high pressure gas venting out, you will not be able to detect it. Now you can place sensors, right? Thermal sensors, but the thermal sensors will be maybe far away from the local hotspot. Okay, so you have a large battery pack, and you have sensors at multiple locations. But the actual hotspot initiation may be happening at a location which is far away from the sensors. Okay, so that may not be sufficient. So and there is thermal inertia of the whole body, so that also will delay this surface heating sensing, right? Then you have pressurized flammable jets that will vent out. So what happens is as these guys disintegrate, right? So as the electrolyte disintegrates and these reactions are happening, now battery is a closed sealed object, right? A cell. So what happens is as these gases are releasing, okay, and as the temperature increases, the electrolyte also starts to vaporize, okay, liquid to vapor. So inside this closed canister, now you are developing pressurized gases, okay, which are also combustible. So at a certain time, once the pressure exceeds the holding pressure, you will basically start venting out, creating a high pressurized jet, which is again a gas jet, which is again flammable because you have all sorts of hydrocarbons and oxygen oxidizers coming out. So what happens is your process of extinguishing becomes very difficult because now it has everything is happening internally, and externally you are just seeing a gas flame. So if you use some kind of a like a water mist or a water jet to reduce the temperature, to bring the temperatures down, so you can extinguish the fire initially. But what happens is still once the battery has lost its structural integrity, still now there are internal reactions that will be going on. Right, your electrolyte decomposition, these electrolyte cathode reactions might be still going on internally, even though we have reduced the external temperature. Okay, so once you do that, what happens is after a certain time, probably 3 hours, 4 hours time, this will again start to burn. Okay, so that is the challenge. So the problem of reignition is very high in EV fires. Okay, so now let's look at some of the. Now we have understood what is the mechanism of the heat generation that is happening inside a battery and what leads to that heat generation. Now, if you want to build a small, simple model, okay, so to basically predict this behavior, so what we have is the heat generation rate due to two reasons. One is ohmic heating because of short circuits, which you have large flow of current. Then it can lead to I square R, so like resistance heating can take place. Also, there could be exothermic electrokinetics. So all these electrolyte anode reactions, electrolyte cathode reactions. Because of those, you will have exothermic reactions. Now, if this heat generation rate is greater than the heat removal rate, then you start accumulating heat inside the cell. The temperature increases, and it ultimately leads to a thermal runaway. Okay. So now, if you now look at this kinetics, so most of the heat is going to be generated because of this material degradation and reactions. Okay. So if you recall yesterday's reaction rate expression, okay, so you can basically express this heat generation component in terms of a some Q naught times exponential of minus EA by RT. Okay, so what was EA yesterday? Activation energy. So that basically says that till you reach a certain temperature threshold, okay, this heat generation will not take place. But once you go beyond that temperature threshold, it will immediately start releasing the heat, or the reactions will basically get triggered, and you will now have a chain reaction of heat generation, high heat release. So what will happen is a very small temperature rise can cause sudden failure, because your heat generation will suddenly increase and your heat extraction is not efficient enough. Okay, so again, this is where the kinetics comes into the picture, for even for modeling battery effects. And ultimately, what we want to do is, if you look at this equation, so your mcp dt by dt, so this is the temperature change with respect to time, will be equal to the amount of heat that is being generated because of the kinetics minus the heat extraction. So now the battery is exposed to some kind of a cooling system, or it is present in ambient air. So because of that, there might be some convective or conductive heat losses that is happening. So now, if the heat generation rate is happening much faster compared to the heat loss, then you start to see a increase in the temperatures. Okay, so that will ultimately lead to your battery failure. Now this is a very simple model, but you know that this is basically representing one reaction. Okay, one expression for the overall heat release rate. But as we saw, the process is complex, right? It goes through these multiple steps. Now, to have a more accurate model of these battery failures, you need to have these kind of detailed models that can basically represent this whole process. The more accurate your model is, it will be used more effectively in terms of battery optimization, like battery pack optimizations. Okay. Again, like to model these accurately, you have to know what these processes are, which are still being explored. Okay, so basically, once your heat rejection is slower than your heat generation, you start accumulating heat, and it will ultimately lead to thermal runaway failure. Okay, so now what happens is, like one of you asked me, what happens if we detect the material quality. So some of the processes that we use, or the approaches that we use to basically monitor the health of the battery, okay, during usage. So one is local heating. So once these kind of reactions take place, it will start to heat up, and the detectable signal is, so either you can put a thermocouple or some kind of a temperature sensor and you monitor the temperature, or it more effective is to look at the rate of change of temperature. Okay, because your heating takes place exponentially fast once you cross that energy barrier. Just looking at the temperature changes may not be a very good signal. Looking at the rate of change of temperature may be more appropriate in basically detecting these kind of things. Then, because of these exothermic reactions, there might be some gases that are being released that will be vented out. So looking at those, so you might have some sensors looking at these trace gases that are being released at the initial processes. Then, because of internal short circuit, if you are continuously monitoring the voltage, then there might be voltage fluctuations when these things happen. All right. Then there could be pressure sensors because of venting. So if you look at the internal cell pressures, you can, if you see fluctuations in pressure, then you can see that think that there are some gases that are being released. Okay. So sometimes you see your battery swelling up, right? These are all indications of some kind of processes are going on where your battery is losing its performance or its integrity. And then there could be material cracking, right? So like once you pressurize your cell, it will suddenly vent up. So if you have some kind of a acoustic receiver, then you can, based on that also, you can detect. But there are disadvantages, right? So when your vehicle is running, you will have other kinds of acoustic disturbances coming in by the sensors. So this may not be a very effective approach for, especially for EVs, right? And again, like putting pressure sensors inside every cell, that is also impractical, right? Because you have thousands of cells that are connected in a battery pack. So there are different challenges that are associated with each of these. So most likely we are kind of using the temperature sensing. Okay, so and we are still trying to characterize the temperature behaviors to battery failures. Still a lot of research is going in that. So the physical sensors may be very limited due to its location. Okay, and it may have a low response time. Now recently there are optical based techniques that are coming out. Okay, some kind of IR absorption sensors, that can basically detect some off gases like CO, H2, CO2 that might be happening in the initial stages of your battery failure. So, and these are typically fast. Your optical-based techniques are very fast in terms of response time. So, they could be one of the solutions that could help us integrate these kind of safety features for batteries. Okay, so this is one aspect. The second aspect is basically the ambient conditions. Now, as we saw, most of the investment is going in India is towards integration of battery into some kind of two-wheeler, three-wheeler. But we are not testing those batteries under Indian ambient conditions because in India, overall, the average temperatures are slightly higher, right? So if the average temperatures of the ambient are higher, then if you look at these equations, the heat transfer rate, that the rate of heat transfer rate in which the batteries will lose the heat is going to be lower because these guys are high. Okay, and because of high overall ambient temperatures, very small amount of thermal overheating kind of things can also push the temperatures beyond that activation energy. Okay, so it is very important to basically look at ambient conditions in India, test these batteries for Indian conditions, especially that are being used for two-wheelers, three-wheelers, and then certify them for usage. Okay, so the other aspect is also the drive cycles that we use in India. So in Western countries, the drive cycles, the urban city drive cycles are very different than what we have. We have lots of braking, acceleration that is needed, whereas the drive cycles are relatively smooth in those countries. So because of that, you are again loading the batteries in a different manner. So how your battery will behave in these kind of drive cycles is also going to be very different. And so that is why we need to have a very good testing and explore the behavior of batteries under these local conditions. Okay, right? So there is the research gap that currently exists is basically understanding the battery failure behavior through battery chemistry. Now, if you are changing the electrodes, changing the electrolytes, the battery chemistry itself changes. So once the battery chemistry changes, your activation energy, those components will change. Okay, so understanding that is very important field of research. Then how you arrange individual cells in your battery pack. Okay, so that your heat extraction or cooling down of your batteries are efficient. That is again an area where research for thermal management needs to happen. Then again, finding effective suppression technology. So just dousing your batteries with water does not help because it is going to damage the electric circuit. And also you have chances of reignition of battery after some time. So again, like what kind of suppression methodologies can be implemented that basically extinguishes battery fires effectively is still an area to look into. And finally, early detection methodologies. Okay, so for battery failures is again an area, especially looking at the material integrity of the battery and associating it with battery health. So these kind of areas are still ongoing, and we will need it because we know that uh, the rate of growth of EVs is going to scale very quickly. Okay, for especially for India, we have lot of users, right? We have lot of users, and we have started implementing it into two-wheelers. Okay, so the number of batteries that are going to be around us is going to increase. So yes, it is going to be very essential to understand these aspects and apply them to our Indian scenarios. Okay, all right. Thank you all. Yes, so those are relatively still smaller batteries, right? One cell or two cell batteries, right? But when you look at and that they are not undergoing as high loads as EVs. So in EVs you have a much more much more cycles, heavy currents are there, heavy current usage is there. Also you have number of cells are more. So if one cell burns, then the damage and the scale of fire is even larger. Okay. So the risk factor, if you want to say, so risk factor is basically a combination of what is the potential damage that will be caused times the frequency of the occurrence, accident occurrence. For mobile phones, it is much lower compared to battery, like EVs, right? Because your potential damage is much higher. Okay.
At the same time, sir, nowadays EVs are also charged with we are putting the brakes. So will it pose any problem?
No, that should not pose a problem unless again like so it is still a charging cycle. Right, you have now fast chargers coming in where you are loading
While
it.
you put brakes,
Yes.
once again the battery gets
Yeah,
charged.
that is regenerative charging, right?
Regenerative.
So that should not be a problem if you are monitoring things for extreme conditions. So that charging rate is still lower, slower than the conventional externally charging systems. Okay, but yes, thank you.
So what is the time limit between the temperature
Yeah, so it can happen in a slow process, probably over minutes, like say like 1 to 10 minutes or 30 minutes kind of time. But it happens slowly, so the heat gets accumulated slowly. But once that separator breaks down, then things happen really fast. Right, the separator when it breaks down, then there is a instantaneous change in temperature. It does not happen like initial processes are so. But probably the first 2 3 processes are so. After the separator breaks down, then the process becomes really very fast. So probably in like under a minute or couple of.
and sir, what are the gases the hydrocarbon?
Yes. So okay. So I don't know if I mentioned it, but you have like gases like which are combustible. Like you will have hydrogen coming out through gas. So some of the hot gases that comes out are like carbon monoxide, hydrogen, CO2, even some ethylene, acetylene kind of molecules are also hydrocarbons will come out, which are very very reactive. So once they come out, they are now exposed to additional air. Right? The initial combustion does not depend on external air. Right? The initial combustion that will happen inside the cell. Once it comes out, these gases are coming out at high temperature. They will mix with the surrounding air and they will burn. Okay.
As an extreme is the fire and the fire. And that another thing that is here when we put it on a fire related on that and then gas practice to the water. So that the air supply, the oxygen supply will be very sufficient in that kind of
Yes. So again, like your initial fire like extinguishing will work, right? Because you are cutting off the what do you say, like the ambient air, and you are bringing down the temperatures, right? Temperature of the batteries. Okay, but internally, so those are external temperatures. Internally, there might be some reactions still taking place. So once you remove those things, if you stop putting water, now you remove the blanket because now the fire has extinguished. There could be internal reactions that can be taking place over hours. Okay, and that will again lead to a reignition because internally there are oxygen molecules available, hydrocarbons available. Right, so internally those can again lead to reignition of the battery.
What is the optimum temperature inside the bag? So at 59 degrees, it just starts fading.
It starts to fade. So typically we try to maintain it 50 degrees Celsius, 40 to 50 degrees Celsius, using some kind of
Yeah.
yes.
In summer, our ambient
Exactly. So that is why you need to have some kind of a cooling mechanism. Usually you have some kind of liquid cooling or air cooling system going on to maintain the
तो ସେଥିପାଇଁ ଆମର ଗାଡି ଗୁଡା ସବୁ ଥଣ୍ଡାରେ ରଖିବା କଥା ନାଇଁ sir? Because there park the vehicles in our offices, we park the vehicles outside under the sun.
Yeah, it is better. It is better.
And in the lunch hour, once again we start and we go the same.
What we said during the charging time, we should park it in the shade, not in the direct sunlight.
True. Absolutely. You should always maintain low temperature conditions. And again, during the charging time, because if your battery integrity is not great, then the resistance is high, you will keep it up. So most of the accidents actually what happens is these two-wheelers, we don't use it, but electric two-wheelers are there like scooters. So they have a handle and you stand on it and you go. So those are widely used by students in universities abroad. So they will basically take it to their rooms and charge it like what we do in like to our mobile phones, and then they'll sleep. And now because these battery racks are not well designed, so they will be basically failing during the charging cycle inside the room. So even if it is inside the shade, temperatures are low again. If the charging circuit is not well designed, battery is not well designed, then it can lead.
Sir, in this last point, material cracking, you said that acoustic signals may have errors. So maybe if we use strain gauges, then because if there is a cracking, then there is some type of deformation.
Yes.
So strain gauges are used instead.
Yes. So those are again like how do you integrate them? right? So now you are looking at an individual cell, and this guy is expanding or deforming, right? But now in the battery pack, you have thousands of these cells, right? How many strain sensors are you looking at?
Yeah.
So that is the challenge. All right. So yes, but if you can come up with some kind of a optical method of looking at deformations, right? So then it might be really useful. Yes, but acoustic signals again, there is this noise from the ambient. Yeah. So like I think that they relate that warranty to the mileage or the
Charging cycle.
range that it will not be great. Okay, so again, you have to trust them and buy it and use it unless we start to see actions. I think in Ola we saw a lot of failures happening.
Whenever the failure happens, then blame it on the customer.
Yes. So we try to shift the blame so that that happens, but we need to be very careful when we are getting these EVs, even from OEMs. They need to test it properly before they supply to customers. Yeah.
Same logic is applicable to batteries of inverter because that catches fire in the houses. Mostly that is very common in Pune, Mumbai, Maharashtra region because of the power failure, power failure.
So the process might be different because it is a different architecture of the battery that are being used.
But how to identify that problem or maybe the
So for those, again, like if you are looking at the current cycles that is being drawn or the resistance, internal resistance of those batteries, so those things will give you an idea about what is the health of the. So typically during charging, what is the energy that it is able to contain? How much time is it taking to fully charge? What is the temperature of the battery that is taking?
yeah, because in my house we are having a battery unit under the granite platform.
Right.
So 1 year back, that platform gets heated every day 24/7.
Hmm.
So after few months, we just went to that battery person and asked him.
Right.
So he said maybe your battery is not in the condition.
Right.
You need to change it. But because it is on the platform, we come to know that it is going to heat and now it is continuous.
Yeah,
for
typically
1
you have
month
to
or 2 months.
have better ventilation so that it does
Yeah,
not
ventilation
overheat.
is there, but it started.
Okay, because of
Automatically.
looking at the temperature
Yes.
you
And we are
realize.
just keeping our hand on the platform and we just realize that heat. And after some time,
Yeah.
change that pattern.
Again, that is again happening because of like some kind of internal resistance is increasing, and
Yes.
that is leading to high region.
But in some houses, it is on the lawn. And nobody is looking at that battery and the inverter.
Right.
So one of my relative got fire in the inverter
I see. Yes.
at the
So
lawn.
all these things are again combustible. So other ones are like these power packs that you get, like solar panels. I just to do a power pack inside or inside the houses. I think Elon Musk had some idea about that. So again, those are also combustible,
Yes.
and we have to be very careful.
Yes.
And now, like inside domestic environments, the number of batteries are going to increase. So someone is parking the vehicle in the parking lot and charging, and those can be triggers to ignition processes.
Thank you.
Okay. Okay. Thank you all.
Maybe it's a